So this side is the GAN participants, like, am I correct? And that side is the MSc people. Okay, I know you well. Okay, so how many of them are here?
25 from outside.
Okay.
The rest are from inside.
Okay, so may I know that can you show me the hands who are GAN registered participants, but who are from here inside IIT? Okay. Okay, and rest you are all from outside. Okay, so out of you, how many are from this state, Madhya Pradesh? 2 and 3. Okay, and the rest are from others. Okay, so I think that your so far things have been very nice. So are you tired of? Okay, so it's a lot of classes going on, and this thing. Okay, so what I thought that after Oliver teaches, this for chemistry catalysis on visible light catalysis, I thought that why not we start with some, other aspects of organic synthesis that we feel that which is also sustainable, and also we should go ahead knowing this because everything stands. Today we talk about visible light catalysis, even infrared catalysis. But we should not forget the traditional catalysis what we have been doing. For example, we cannot forget how Lewis acid catalysis have helped us a lot in throughout journey of the organic synthesis. So when I talk about a throughout journey of organic synthesis, I would like to highlight that how we have been going all through these years. Can you close that door? How organic synthesis have evolved. That is also a very big thing. What as a practitioners of organic synthesis we should know. Okay. So if you see in the slide I have made, I'll start with the first few slides stating that we think about knowledge on retrosynthetic nomenclature. So these are some knowledge competences what I feel that a student must have when he talks about or we think about organic synthesis and catalysis. And then we come to asymmetry. So I feel that a student should have knowledge on retrosynthetic nomenclature, knowledge on mono and multi-dimensional retrosynthetic strategies, knowledge on interrelations between retrosynthetic entities and real chemical compounds, knowledge on designing synthetic routes to complex target molecules on the basis of retrosynthetic considerations. See, I always say my students, whoever have been doing or studying with me or carrying out different journeys with us, that whenever you after your training, you join academia, industry, wherever you join, the first thing, even I have told to our master students, that the first thing what your employer or your exact supervisor wants is a complete trained student. Okay, this is what is the expectation. You may pursue your education in India or in abroad. You may work in academic research institutions or you may work in industries. So what is an expectation? As a synthetic organic chemist, people expect you to be very, very competent. When I say it's competent, it means that there is something called a toolbox in you. What is a toolbox as a chemist? As a chemist, the toolbox is the vocabulary, the knowledge you carry on. I've given them examples. For example, the moment you join industry and they ask that you need to make this molecule, you go to the fume hood and get a very economic strategy of this molecule. And that is the point where time matters. You cannot say to your supervisor that, okay sir, I will take 7 days to design a retrosynthetic analysis and on the 10th day I will start the first reaction. And at the end of 1 month, I try to give you that molecule. So this is not going to work, okay, because we think about time economy. And there, the time comes where you need to understand that how beautifully you can do a retrosynthesis, how beautifully you are trained with a toolbox of reagents. The moment are going to use sodium hydride for a reaction, or going to use potassium hydride or lithium aluminum hydride, it should come in the first sense. So I want my students as practitioners of organic synthesis who take these courses that you should try to come up there where there is no time. The moment I say you that I need a reagent to go for a reduction of an alpha beta unsaturated ketone, keeping the double bond intact, you should tell me immediately, sir, this is the reagent. The moment I ask you that I want to maintain the stereochemistry intact when there is an alpha chiral center and then reduce the double bond, the moment I say you, there should be something in you where you come up, okay, sir, we are going to choose sodium cyanoborohydride for this. So this is the place we want our students to come up. Okay, so with this basic introduction, I feel that these 4 portions, the 4 points, what I feel that the competencies may generate among our students are retrosynthesis, multidimensional retrosynthetic strategies, interrelationship between retrosynthetic entities and real compounds, and also designing very, very complex target molecules. Okay. Now, what are your performance skills? What I believe that we should grow up? They are recognition of distinctive structural patterns as key elements for retrosynthetic disconnections. In the third point, see, I have mentioned that there should be a strategic decision making based on structural features of the target molecule. See, it's a feeling, it's not memorizing. See, chemistry is a feeling. You should feel it. You cannot think that I set a reaction in a fume hood and I'll go to the hostel, ये 8 घंटा घूमने वाला है, मैं जाके सो के आ जाता हूँ. No. So there should be a feeling. It's like your baby. Okay. When you set a reaction, you feel that what is happening? Is my baby giving birth? It's growing. If growing means is a new molecule gets generating. See, you are very powerful. So who is the most powerful in nature? Mother. Okay. And how you are powerful? You are powerful because you have the art of making molecules. You can give birth to a new molecule. Okay. And I say that as babies have brains, molecules also have brains. Otherwise, an antibiotic cannot go and selectively kill certain cells and do not kill the other people. So those are molecules. So I feel, I perceive and I believe that molecules have brains. They can understand where to go up. Okay. So it's growing of your babies, which are molecules, giving birth to them and then reacting. So it's organic chemistry is a feeling, and it starts the moment you start doing the reaction. Okay. Now, so this is some of the concepts, background and terminology what I feel, and we'll go like this. We have a historical overview, we have taxonomy of retrosynthetic analysis, general aspects of retrosynthetic analysis, categorization of retrosynthetic strategies, retrosynthetic analysis of aliphatic and alicyclic compounds, and retrosynthetic analysis of aromatic compounds, and analysis of variant natural products. And I want it that when I go through, it should be interactive with you. Okay. So these are some of the stalwarts, I believe, that who have written these articles and books. They have been highly cited, and I think that every one of you should have a look. The first one is a very good collection by none other than Professor Elias James Coe, and this is the logic of chemical synthesis. Okay. The next one is, I think many of you have already read. The next one is organic synthesis, the disconnection approach. So how many of you have gone through this book? Can you put your hands up? Okay, I have gone through. No one? So this is, I think this is available, and this is already being taught in many of the undergraduate syllabus. So this book is a very handy book and gives you an understanding how you should try generating or synthesizing molecules. The third one what I have enlisted is a paper in Anglo one day by E. James Coe in 1991, where he shows very typically very strong molecules or very complex molecules to synthesize. And you see, it starts in 1991. The moment I'm talking about this time when we did not have lot of structural analytics. Today we have single crystal XRD, we have high power NMR, 600 megahertz, 500 megahertz, what not. But just try to believe that in 1991, when people used to do all these complex molecules, how they are doing it. Today, even students need just perform a one step and they run for NMR. I want you to also remember those time when organic synthesis grew and we did not have any tools of characterizing these big molecules, these complex molecules. The third one is by Walker in a very common article. This you should also go through this. And the last one, what I feel is very important, is a fantastic article in Agrande by none other than Casey Nicolau. Okay, so I hope that these 5 articles, whenever you get time, you should pick up and go through any of these articles in your leisure time. Believe me, they are very nice, very informative. Okay, a short history of synthetic planning. You know all that Corey has thus been awarded with Nobel Prize for 3 intimately connecting contributions which form a whole. Through retrosynthetic analysis and introduction of new synthetic reactions, he has succeeded in preparing biologically important natural products. So he was really, fantastic. If you see Corey's contributions, then it's unimaginable that how this guy could do this type of chemistry, 100 years back. It's something which was told by Professor S. Gronovich, and who announced this during 1990s Nobel Prize Committee of Chemistry. So he told these few lines in honor of him before he was awarded Nobel Prize. So I feel that it's Elias James Corey whose contributions or whose findings laid the 19th century synthetic chemistry. What we have been doing now is just piling up on him. Okay, our contributions are really great, I'll say, but everything we can build on certain foundations. So one of these foundations is by Professor Corey, and in today's world, if I remember a young guy, then I will think of Phil Barron in the US. So I think these 2 people have shown some or given us some important pillars of organic synthesis. Okay. So if we go in the phase 1 in the 19th century, we can remember that these molecules, what are these molecules? Hohler in 1898 discovered urea. We all know urea today, right? Followed by Kolbe. I think, see, what I'm mentioning is some of, how we progressed in organic synthesis. And at the end of the time, I think you can correlate where we started and where we are. So it was our first achievement in 1828 with urea, I feel, followed by Kolbe's synthesis of acetic acid in 1845, and then comes Fischer. So you know Fischer? There were 2 Fischers, interesting thing. There were 2 Fischers. One is the Fischer who discovered glucose, and there was another Fischer. Who was that? Sorry? Fischer projection. There was, what happens? There are some competitions. So in batches, when we did masters, we had competitions. My friend used to think that I'm a better student than him. He used to think I'm a better student than me. ये natural है, ये होता है. And these 2 Fischers, there are competitions. Both these Fischers always is competed who has first designed the arrow. We do in organic synthesis, right? A arrow B. We do this, right? A, B. So what is A? A is a starting product. And what is this? There is another arrow. What is this? So all these arrows have resemblances, right? Okay. So what do we call this? When we use this? In retrosynthetic analysis. And both these Fischers, they competed throughout their lives that which Fisher developed these arrows first. Okay, and this was one competition. Another competition was between Woodward and Fisher, that who actually designed the structure of chlorophyll. Okay, so all these competitions are happening and they're healthy competitions. Okay, so it all started from very beginning. So how do I erase it? I don't know. Can we erase it? Okay. Okay, thank you. Okay, so we started with reactions designing anthracene. You can see this, this is anthracene, okay, and small oxidations like potassium chromate, sulfuric acid, we generate alizarin. So if you see, the key features are that synthetic organic chemistry focused on the analysis of simple intern conversions of small molecules and coincident discoveries. Very little structural information available those times. So you can see that I have given a journal, I collected this from this journal in 1869. So only empirical formulas. So we started our journey as synthetic chemists from here. Okay, it's the earlier 19th century. Also, we find that we generate molecules, we generate synthesis like ammonia and oxyacetylnitrile, hydrocyanil and hydroxycyanide and giving urea. So these basic transformations were the one which were carried out during those times. Okay, I'll quickly pass to the next one. When we started going towards some more complexities, like the one I showed, that anthracene you oxidized with potassium chromate and sulfuric acid, and now we were in a place to understand what is actually alizarin with the help of the functional groups. Okay, so how do you understand functional groups without NMR? How can you do it? How can you understand that there is a group called carbonyl, there is a phenolic OH, and I say you that you have nothing in your hands. You don't have IR, you don't have NMR. How you are going to find out? Because it was not available in this time. People were understanding that the chemistry was dominated by aromatics, particularly from coal tar. Now, I tell you a very important information. Try to understand. Today we are in a position where we should shift our chemistry. Why I say that? Our chemistry was always oil driven. Is that correct or not? It's oil driven, because what we come is all non-renewable resources. So you generate hydrocarbons and then try to functionalize these hydrocarbons. And what is the source of these hydrocarbons? The source of the hydrocarbons is always an oil. Is not so? You get everything from oil. You try to understand. But where we stand now? So there is a time that we change our chemistry. We change our chemistry from oil-driven chemistry to biomass-related chemistry. Is not so? We should come up, right? Because we know that 10 years, 15 years, 20 years, what will happen to us after 25 years when the oil is gone? Where you get these hydrocarbons which we want to functionalize? Where you get this, oxidized molecules? Because ultimately the source is oil. Okay, so we started from oil, basically coal tar, and then we tried to functionalize. We did not have NMR, we didn't have IR, we did some oxidations, and slowly a time came, then we started using some chemicals to understand, okay, there is a carbonyl and the chemistry is dominated by aromatics, there is phenolic OH and nothing else. So this was what we were understanding on the phase 1 phase. So this is the first phase of organic synthesis in 19th century. Okay? Okay. Now then comes the early 20th century. Very beautiful time. Why? Because here we start growing up. Okay, growing up. The entire world starts growing up in synthetic chemistry. perfumes start coming up as a very important molecules in Europe. Okay, so we needed molecules, we needed sesquiterpenes because very high demands, particularly in European countries, on cosmetics, on perfumes. So people tried to get new molecules, tried to increase the molecular complexity. And you see, Will Slater in 1901 comes up along with Robinson. So I think both of them synthesized first tropinon. So why this molecule was important? Because we started finding a three-dimensionality here. So we started increasing the knowledge on structural, empirical and structural formulas. Okay, we tried to think on the tetrahedral model. We tried to think on increasing synthesis of non-polar target molecules. So we tried to come towards more molecular complexity. We are no more on urea. Okay, we have started thinking on visualizing three-dimensional molecules which were important to the human race. Also, camphor. We all know why camphor is important. Okay, so these were start coming up. But you remember one thing: we did not start doing multi-step synthesis. This comes later. We started understanding that these were some three-dimensional molecules and that can be used in industry. We started understanding that. Also came up something called the very important one by Fischer in 1929, which is called hemine. And we all know why it is important. Why it's important? Because it forms the basis of something called porphyrins, right? Why porphyrins are necessary? Because we all know what are the bioactivities, what is inside us, who are the oxygen carriers. So it was the first phase of early 20th century, and we call it phase 2 of organic synthesis, where we started understanding these molecules. And please try to understand that we should always understand the contributions. See, Perkin in 1904 developed the alpha terpineol. So we read alpha terpineol in natural product synthesis. So see, we had important contributions by Robinson, Perkin and Fischer. It started in the early 20th century. Okay. Now, if today's world, so we are all equipped with NMR, mass, everything. Now, if I say you that I want to generate tropinon, which was synthesized by Will Slater in 1901, and I give you cycloheptanone, you try to make it. How you make it? So you join an industry, and the same guy who is there in the industry, who is your boss and group leader, asks you, go to the fume hood and make tropinon today, which was synthesized in 1901. And it was done by 16 linear steps. You do it in 3 steps. What would be your answer? How do you think? How do you start thinking it? Can you make it? Can we make tropinon from cycloheptanone in 3 steps? Is it possible? Okay. So what will be the starting step? Any idea? You have cycloheptanone and you want to have 3 steps to make tropinon in 3 steps. And what is the first step I am asking from you? Okay. This is the way that it was made earlier. So you start with a cycloheptanone and you do a reaction like hydroxylamine and then treat with sodium ethanol. I am not going into details, but you see there are a series of steps which gives you something like this. So what will be the name of this? Anyone from the MSc? I want some interaction. Even the early PhDs. What will be the name? So Arindam, what is the name for this? Anyone from your side? What would be the name for the last, we generate a salt. What would be the name for this? shall we call dimethyl aminotropinol chloride, or what it is? Okay. So we keep something for tutorials. Okay. Now, so we generate this salt, heat it so that there is a liberation of methyl chloride, and through these steps, so that I'm not saying you or explaining you all these steps. So there is something, we eliminate, we go for anhydrobromination, then we replace the bromide in sulfuric acid conditions, and finally the chromic acid oxidation gives you this product. But what was important was the last line. Please try to see. Reaction sequences predominantly linear. So they were linear steps. We didn't have stereochemical considerations. So in the phase 2 of organic synthesis, we went into some complexities. We came up with 3-dimensional molecules, but we were not in a place where we started thinking of asymmetric centers. Okay, so what is asymmetric center? What is asymmetric? What do you mean by asymmetric? Anyone? So do you know what is asymmetric? Anyone can put your hands that, yeah, I know asymmetric. What is an asymmetric center? Okay, yes. So he says that it's a designated chiral center. When is its chiral center? Then what is a pro-chiral center? So we generate an asymmetric center from a center which is not chiral, is a pro-chiral center. Is it like that? Okay. Now, so Robinson in okay, can you see the yellow color? Okay. Robinson in 1917, he said that by imaginary hydrolysis at points indicated by dot lines, so there were some dot lines here, okay, and the substance may be resolved into succinylide, methylamine and acetone. So he said in 1917 that if I plan to make tropinone, first I should try that where I should cut the bonds. Okay, so this was something what Robinson planned in 1917. He looked like, so there was nothing called retro. He imagined, so it's an imaginary hydrolysis, that if he thinks that if he cuts these points, okay, you generate something like an aldehyde, methylamine and acetone, and this suggested a line of attack and nothing else. So the first thinking of retrosynthetic analysis comes in 1917 from none other than Robinson himself, who started thinking that how to break a tropinone. And in the process, he thinks that he generates an aldehyde, methylamine and acetone, and that is nothing but an advent of retrosynthetic thinking. So if I ask you that when did we as a chemist started thinking the concept of retrosynthesis, then it's nothing which comes with Robinson's thinking in 1917. So we should be clear with our developments. So it's 1917 which taught us, which was the first idea that, okay, if I cut the bonds of tropinone, which was actually synthesized long before by Will-Slater in 1901, but all these 16 years, no one thought what is retrosynthesis, how to cut the molecules. So it was first by a very big shot, Robinson. It's 1917. And if you search in Google, as I told you, that there has been always competition between chemists. If you search something by typing, competition of two Roberts, then you will find one is Robert Robinson and the other Robert you should find out. Okay. So there were two Roberts who fought each other in telling the world that who has first synthesized steroid. One is Robert Robinson, the other one you should find out. Okay. you should also do some activities during your Gyan course. Now, what he actually meant was, if you have this aldehyde and a methylamine and you do a one-step reaction, then you should end up with something like tropinone. Okay, this is an one-step transformation which was planned by Robinson in 1917, and this is where we successfully tried to cleave the molecules and make the molecule and understand that, okay, this way we should approach any molecules to be given us. Okay, phase 3, the mid of 20th century, and we call it as the phase 3 of organic synthesis. What do you see in the slide? We started with urea, right? The human race started with urea, and now if you see all these 5 molecules, a name has been written in the end of this molecule. Who is this guy? He's a guy who died early, but did a lot things that we did not have a second Woodward in the world. Okay, so he's a guy who was already awarded Nobel Prize in 1965, and his name was Robert Burns Woodward, and he tried to go for structural elucidation using IR and NMR spectroscopy, combustion techniques, melting points, ultraviolet techniques. But see that from where we migrated, we were thinking of tropinone in 1917, and in the mid of 20th century, in 1944, 1950, 1951, 1954 and 1966, an antibiotic comes forward with Woodward, which we use till now. It is cephalosporin C. This was a point where we started using plus minus. What is this plus minus? Plus minus is what? Racemic mixture. So now you please try to understand that this was a time. So by 1944, we started understanding that there were something called racemic mixtures in the molecules. Okay, so we tried understanding the stereochemistry slowly now. We are getting the masters. We are becoming the masters of chemistry, understanding that these are complex molecules. See what was strychnine, so complex, and it was Woodward in 1954. How many chiral centers? 1, 2, 3, 4, 5. He tried synthesizing these molecules in his lab with his group of students. See cephalosporin C, very tough, because you have a 6-membered and a 4-membered lactam with it joined together. We can easily synthesize it today, but in 1966, with limited facilities and limited reagents, Woodward was the person, and his lab was a group who synthesized all these challenging molecules, starting from quinine, cortisone, strychnine and cephalosporin. So this way, from 1944 to 1966, Woodward's group in the US was a group who actually pioneered the synthesis or completed the synthesis of very, very complex molecules. This is a place, this was a time then really the synthetic chemists were always in the show throughout the globe. Okay, everywhere they were treated as kings, because just see their perseverance, see their hard work. All these molecules were required in the globe because these are all biologically active. No? This quinine is a very important, pharmaceutically important drug, and the whole world wanted that. So how we are going to get it if the synthetic chemist is not designing strategies to get it, because natural resources are less. Okay, so this is what happened in mid 20th century, and we started understanding that there were stereogenic carbon centers. So these were the carbon centers what we tried to visualize. Okay, stereogenic carbon centers. Okay, very good. Now if I ask you a simple question, I have a starting point like isoquinoline 7-ol, and you are a student of Woodward in 1944, and you need to make it. And your boss says that, okay, you need to make this molecule. How are you going to make it? You have to make it, otherwise you will not get your PhD. How you are going to make it? Okay. So there we start thinking synthesis planning was markedly guided by degradation studies, a standard candle, what I call, along synthetic route. So it was like a candle, okay, and it was giving some light out of the darkness, and it was guided with building blocks, okay. So it was nothing like creation of these beautiful steps. So we started understanding that, okay, this way we are going to break the molecules. We start isoquinoline, then N-methyl isoquinoline 7-ol, then a dearomatized skeleton and a quinonucleotide precursor, finally heading up to quinoine. So this is what is the starting material, what Woodward wanted to do, and then go towards this. But I would say that if you read Woodward's paper on this, their strategic rationale still remains unclear because there are many other alternatives. So the only thing is what we can understand that this is not the best synthesis what Woodward had prescribed in his paper of quinine. There are many other simultaneous syntheses, but I feel that personally the reagent availability or the availability of the starting materials in the US in that time in 1944 had restricted him to go all the way around in so much of tiring reactions. Okay. Today we want to synthesize a strategy which is of any molecule which will be easily accepted by industries. See, industries are not going to accept you like anything. They raise questions on your retrosynthetic analysis, that how economic it is, how fast it is. In our laboratory, we think of a reaction called dearomatization. My students are sitting here. We think that we need the reaction to be done in 10 minutes. We cannot compensate 2 hours for it. This is the scenario today, but we have not reached in one day. It is all through all these years that today we are discussing the past because we need to understand the present, where we have come through. Okay. Now, so just a question that if this is not the strategy, okay, we start from isoquinoline 7-ol and then come to quinine. So 1, 2, 3, 4 and 5. If this is not the strategy and you use the same starting material, and if I said it's 2 steps to this, what would be the reaction? Did you get my question? My question is, this is the starting material you're using, or isoquinoline 7-ol, and Woodward has given 1, 2, 3, 4 steps. I want to do it 2 steps. This is important because I'm going to raise a question on you for examination. We will be doing grading on that. So 2 steps. So Sangeeta will be sharing the slides. 2 steps starting from isoquinoline to quinine, not all the way around, because I have already told you that the rationale by Woodward remains unclear, that why he has used long, So please find a strategy in your minds, or you practice, or you whenever you complete the course today, just think of this reaction which will be completed in 2 steps, not all these steps. You start from the same material, starting material at isoquinoline 7-ol and reach quinine, but you can use only 2 steps. This remains a question to the Gyan students. Okay. Now, the phase 4 of organic synthesis, you see extraordinary complexity of molecules. Can you see the molecules here? Elias James Corey, Kishi, Nicolaou Corey. See, I often love to tell you stories to all my students. Tetrodotoxin is a molecule. So if I ask you what is the most poisonous molecule in the world, what will you say me? What will you say me? Yes. What is the most toxic molecule in the world, available in the globe now? What will you say me? Is it potassium cyanide? Is it potassium cyanide? Sorry? Is it potassium cyanide? Many people, many students say me, sir, it's potassium cyanide. You just take it in, 1 minute you're gone, because it traps all the oxygen and, it removes the coordination of oxygen, okay? Because the cyanide is a better coordinating to your iron in your hemoglobin. So it's not. It's the one molecule which is synthesized by Kishi. Yoshi took Kishi, and it's called tetrodotoxin. It's available in the skin of the puffer fish. So this molecule was designed or synthesized by Kishi in 1972, which is actually the most toxic molecule known till today. And they have a fantastic relationship. Kore and Kishi, I'll tell you why. But before that, you see the molecules, Nicolau, see the, it looks like a basket, isn't it? But just think that how to make this molecule, very tough. See the number of chiral centers, just see that imagining this molecule is so complicated. And if I ask you to design a retrosynthesis of this molecule, how complicated it is, and when it is in 1988, it's not in 2025. So try to understand that how people is to, first you need to visualize the molecule, understand the structure, chiral centers 1, 2, 3, 4, 5, 6, 7, 8, so many chiral centers. So if you have 8 chiral centers, how many enantiomers you are going to have? 2 to the power 8. And out of these enantiomers, 1 is pharmaceutically very, very active, which shows you those properties. And you need to design a retro which will exactly synthesize this stereochemistry. Okay, the relationship with Kishi and Kore is that Kishi was a researcher in Japan, and the moment he delivered his lecture of tetrodotoxin in a conference, that how he made this complicated molecule, and after his lecture, Kore was so happy that this young guy has done completed synthesis of so strong molecule, he immediately offered him position as an assistant professor in Howard University. And from that time, Kishi is still now, he is in Howard University. Okay. I know all this because I am a student of Barry Trost. Okay. Barry Trost is in Stanford. I did my postdoc in Stanford, and Barry is also very old. Okay. So he was actually in touch of all these people, and I used to see that these people used to come there and visit and all that. So I know the stories from that time. Okay. So Kishi it's just because of this molecule when he synthesized and he showed that he made it. Then Kore was so happy with his work that this young guy could do such a complex molecule. He's deserved to be in none other than Howard University for his rest of his career. So it's your work which gives you a lot of recognition. Okay. Now, so you need to increasingly, so at this moment you need to understand that we have started the sophisticacy in the molecular design. So we were entering the sophisticated era of molecular designing. Okay. So just as I told you in my starting of my class, just imagine that how strong you are. Okay. How strong you are because you are a person who has the capability of making this molecule. The rest of the world doesn't have. Okay. Now, the key questions. So, what has raised in my mind, and I have taken up these questions after I went through the logic of chemical synthesis by E.J. Kore, and I think these questions will rise in every one of his mind. The questions are: how does modern toll synthesis differ from historic approaches, and what can we learn from that? How do we rationalize the synthetic approach to complex molecules? and what are the guiding considerations when planning a synthesis. Okay. So I'll just take 2 minutes to ask any of you if you want to answer that. So in the last 27 slides, okay, what do you think? How does the modern toll synthesis means the same thing. You start from a small molecule and reach a complex molecule. How does a modern toll synthesis differ from the historical approaches? What do you think? Anyone from MSc? How do you think? You went through the last 27 slides and you also saw that what I have done a gist of everything, a summary of everything, because if I catch one phase, each phase of organic synthesis, that itself will take 4 or 5 classes. Okay. So how does toll synthesis differ from the historical approaches? What do you think? Today's approaches. What? Any idea? You should think. The first idea what I feel is that, and that is sustainability. Don't you think that we, as I mentioned you, that we are going short on our raw material supply because we are going short with non-renewable sources of energy, and all this synthesis, all these starting materials, whatever chemical companies it can be Sigma All Rich, whatever it is, they are supplying us starting materials which actually are derived from these oil-based chemistries. And this is a place that we need to shift our paradigm from the oil-based chemicals to biomass, because biomass is glucose, furfuryls, oxycycles, pyridines. We need to have those starting materials in the toll synthesis. For example, we need to start thinking that I will pick up some dry grass from the ground and put in a reaction and get a molecule. Or I use this plastic, take this, scratch it and put in an RB and then do a reaction, and we get the next step of a complex molecule. So we should slowly shift off this paradigm from this portion to this. But again, I did not tell you one more important thing. Okay, what I say is this is the raw material I'm talking about, but what about the strategies? If you remember, if you understand, if you try to find a cost of the most employable catalyst across the globe in industries, what is that? And which is that reaction? Can you tell me? Any idea? The reaction, yeah? The reaction is hydrogenation. The reaction is hydrogenation in one side when you reduce a double bond to an alkane, and the other side is, yes, to some extent, but modern industries are coupling reactions. Okay, Higgs couplings, but you use what catalyst in both these cases? Palladium. Different phases of palladium. If you go to hydrogenation, you use palladium charcoal. Did you ever know that what is the price of palladium charcoal? I'll tell you. Can you tell me? Can you tell Sangeeta? What is the price of palladium charcoal we use? Anyone? Ramakant? I tell you. We buy in our lab 10 grams of palladium charcoal, 10%. 10% means it's only 10% of palladium, and we buy with GST 17,000 rupees. We are a small laboratory. Our laboratory has 15 PhD students and master students, okay, and some people. So our strength of our lab is 20 in my research lab. Now just think an industry where 500 employees and scientists are working, only one industry, and hydrogenation they are doing in tons. Just understand the amount of palladium being used and purchased. On the other side, the coupling rate is also very high. You visit any industry. I always visit industries because I have been a very invited. I'm very lucky to be invited to very many industries. I visited AstraZeneca, I visited Middlesex Industries, I visited Anbaxy. We work closely with Dr. Reddy's. We know it. So we have a place now where we need to shift from the reagent-based chemistry or metal-based chemistry to what? To what? Sustainable chemistry. What is that? What is that? That is nothing but light. That is nothing but electricity. So electroorganic chemistry and visible light chemistry. I'm not talking about UV, we cannot use. That's environmentally not allowed. So I think that if we want to rationalize and if we want to understand that where we should shift or how does the modern tool synthesis differ, that's only and only sustainability, so that we should, as a chemist, we should not be called now and a community which uses the solvents and dumps the solvent in the environment which we cannot sustain. We should shift to a place where we should plan all this tool synthesis from a starting material like plastics. This is the point what we need. Okay, very good. So what is the time of this class up to? 3? Okay. Okay, now coming to the general aspects of retrosynthetic analysis. I have like lot of things, so I don't know. Okay, let's go fast. So what is the traditional approach? The one I show in the screen. What is SM? You all know. What is something called a starting material in a chemical reaction, right? And something we give a double arrow and we write intermediate, and then some more synthetic arrows and we call it what? Target molecule, right? So this is something we think of a forward reaction, and Corey says that we focus on something in the process called FG. What is FG? Functional groups. Very nice. You know everything. Very nice. Okay. Now, so the left side is a traditional approach. Starting material, intermediates, synthetic arrows and target molecules. What is the modern approach? We go reverse. Starting material, intermediates and target molecule. So this is what we talk about, the retrosynthetic arrows. Okay, very easy, very nice, we all understand this, and we call it a guiding principle called retrosynthetic analysis. Very nice. Now I come up a question. Okay, you see this molecule, very nice molecule, 6-membered, 2 diketones, 2 esters, fantastic. Now which one is best? I want to make this molecule, and we cut this molecule as A, B and C, because by this time you know how to cut molecules now. And I ask you a simple question, which one would be the best? A, B, C. B, why? Let's find it. Okay. So if we go for A, then we generate some intermediates like this. Okay. So we have a positive charge here and we have a positive charge here, and we have C and minus because they should combine. So it should be opposite charges, right? Is that correct? So this is which comes off after we cut A. Now the next one, if we cut B, what do you get? We get something like this. We have the same thing, we have a negative charge here, we have a positive charge here, we also have a positive charge in the alpha acyl group and negative charge here. Fine. And if we cut C, then we have something like this, which is also intermediate. And I ask you that Arindam says that B is the best. Why? If you see the overall plan, it's nothing. In all these 3 cases, what we try to find is overall plan to reach a final target material, identification of efficient disconnections, and identification of suitable transforms. These are the 3 things we want. And then we have a situation that either we're going to cut the molecule this way, either we're going to cut the molecule this way or this way. Which is the best and why? So your voting is for B. I think Oliver planned very nice softwares. Huh? You are all voting. I have to learn it from you. Okay. So this was B, right? Is it B? Anyone from this side? Is it A, B or C? Which is the best one you are going to choose? Obviously there is symmetry, I understand. Okay, sorry. Which is the best among this, and I need a proper explanation. So I'll ask Arindam. Arindam said it's B. Why it's B? Can you speak louder so that everyone can listen? That's a very perfect point he picks up. He said that if you have a minus here, then actually this methylene is actually flanked in both sides by two electron withdrawing groups, and then this is actually stabilized. Do I find any other stabilization here? Here there is a stabilization, but there is a negative effect. We also have a stabilization here, but we have a negative effect, and the negative effect is having a acyl carbocation, which is actually an unstable one. Okay, whereas we do find it here too, but in both these parts, this is what is actually stabilizing the intermediate B much better than the other two. Is it correct? Yeah. So that means that we need to choose this retrosynthetic analysis because we need to have a very successful reaction. And then what will be your starting material? It's very easy. So your starting material should be someone which has a positive one, which if you have, you can take a chlorides from this side, or you can take a methyl in this side. Okay, is that correct? Or you have any other opinion? Is the B correct? Okay, very nice. Now, sorry, what about this molecule? It's antimicrobial molecule, and I need something like having an hidden symmetry. Okay, what is an hidden symmetry? Just try to have a look. In this molecule, we had an obvious symmetry, which was very, the moment you see this molecule, you recognize it. The next molecule I pick up, I call it that there is an hidden symmetry. The hidden symmetry comes from where? The hidden symmetry comes the moment I cleave this bond, and we generate two double bonds like this. So here lies the point that can you come up with a step which gives you an hidden symmetry while solving the retrosynthetic analysis of a molecule. Okay, so the hidden symmetry is very important. You need to understand that if I can come up with a hidden symmetry so that you can use the same type of molecules in both sides. There are many people, many good synthetic chemists, even Kore Nicolan in India. If you see Professor Alakesh Bishai from IISER Kolkata, you'll find that all his molecules, what he designs, is based on Kore's principle. The moment you look the molecule, it looks very, very complicated. But the moment you find the hidden symmetry, actually you are going to use only one molecule for the synthesis. There's just dimerization. So this is where your perseverance comes in. You need to find out that if there is something like an hidden symmetry in the molecule, and that gives you just nothing, but you just take one molecule, create a positive and negative charge, and thus just dimerize, you get the best precursor to go towards your target material. Okay. Now, the next thing, examples or presence of functional groups, very sensitive to a nucleophilic attack. So, when I say that strategy, okay, we have different strategies to look into the molecules. So, can you see any important functional group in this molecule which I have drawn? And what is that? Can you highlight? Michael acceptors. See, Michael acceptors in organic synthesis have played very, very important role in solving molecular complexities. So, I would like to give a message to all of you that whenever you start your own chemistry, always try to think that can we start a molecule where there is a Michael acceptor, very reactive one. Why do I say this? Because I have personally found it that if you have this type of systems where there is a Michael acceptor, what is a Michael acceptor? Where you can undergo 1,2 additions and also 1,4 additions. And if you plan for a synthesis of big molecule and you are confused that where I need to start, in such cases, having intermediates or having molecules as a starting material which have reactive Michael acceptors is a very, very good choice, because it gives you immense independence to make this molecule very complex. You can use it in any methodology. If you do a one-step reaction for any journal, for any paper, and your teacher asks you, can you go for functionalization? Can you do something in the paper that the research paper looks very interesting? Then I will always choose a Michael acceptor, or rather a cyclic Michael acceptor like this. You do whatever you want to do in your paper, you do. But at the end of the paper, in the functionalization, in order to show a very, very huge applicability of your science, this is what is very important, very sensitive to nucleophilic attack, should be installed in the late stage. What does it mean? It means that it is so reactive that whatever reaction you do, and if you install the system in your molecule, it can show variety of variations. And this is very much required. See, today if you want to publish a paper in Jackson Agrawanda, the first thing is, what is the application of your paper? And how do you show it? You show it in the application when you prove that yes, my methodology can create a lot of important biologically active molecules. But how you are going to do it? You have less time. In such cases, you should use such reactive intermediates. Okay, but how do you make such molecules? And it's not easy to make such molecules which are reactive. Okay. So what is the beauty of cyclopropane? What is the beauty of cyclopropane? The beauty is that you use it in radical reactions, you use it in heat, you use it in visible light, it will open up, right? Why? Okay, it's very open. So Ramakant बहुत शांत लड़का है, he's very शांत लड़का है, and the other guy in my lab is very hot minded, कभी भी लड़ता है. Who is better? आप पूछ सकते हो सर आप क्या क्वेश्चन कर रहे हो? Who is better? Cyclopropane is also like that. To make cyclopropane is tough. Is not it so? But you see the usefulness of cyclopropane. So that means in chemistry, when you want to make reactive molecules, making these molecules is also not easy. So when you think of alpha beta unsaturated ketone like this, we need some specialized reactions like Eisenhower methylation, and it can be done in one single step. You use this, this 5-membered lactone and react, and you get it. Now, okay, very nice. Can you see this molecule? It's quasine, bittering agent. What is bittering agent? Why it is used? It is used in drugs which is prescribed. Many companies advertise them as, you can give this thing to someone who wants to get free from nicotine. Okay, this is the most bad thing what organic chemists have developed till now, what I feel. Although it is very active in entertainment industry, but it's not correct. So quasine is one of the molecules which is prescribed to people who want to quit smoking. Okay, bittering test. But you see the molecules. There are 7 stereogenic centers. How to control them? Do all the stereocenters need to be externally controlled? Now, how do you make this molecule? Because there is a huge industrial demand. Even the ITC wants to make it. What is ITC? Yeah, there are 2. One is Indian Tourism Corporation, the other is Indian Tobacco Corporation. One of the most, So how do you want it? How do you make it? So I tell one of the students, go to the lab and make this molecule. What will be the retrosynthetic analysis? 7 stereogenic centers. How many enantiomers possible? 2 to the power 7. What is the number? I did not calculate, but you can calculate 2 to the power 7 enantiomers, but see the stereoisomers. This hydrogen and this methyl is cis, this hydrogen and this hydrogen is trans, this hydrogen and this methyl is trans, this methyl and this hydrogen is cis, and this 1,3 hydrogen are trans. So you have this molecule, you have to make this molecule, but retaining all these 7 stereogenic centers. So this is one out of these 2 to the power 7 enantiomers which is bioactive, and we say it's configurationally unstable. Why it's unstable? Because lot of chiral centers, you cannot expect that how much stability it gains while synthesis. Okay. So I point something like, I will come to this point again, I think next class or tomorrow's class, something like thermodynamic control. So what is the difference between kinetic control and thermodynamic control? What do you mean? आसान भाषा में बताओ. Kinetic stability, thermodynamic stability. Shall I give you an example? I'll try to explain you in this way. You are standing in a bus stand and a bus comes, and suppose Arindam is standing and the bus stands in front of you, bus is fully packed and there is one lady seat, okay, and Arindam is a male and he is thinking to sit or not. If it's a kinetic condition, he will sit. Now the same condition is, the bus comes, the bus is purely vacant, there is window seat, there is front seat, and then Arindam chooses a window seat and sits there. What is this? This is thermodynamic stability. Okay. Understood the difference or not? The first one is a compulsion. What we call is kinetic stability. And what is the second one? Is relaxing mood, is an honor, is like something, you choose the best for you. This is what is thermodynamic stability. So when I say that the purple one, okay, is something which is configurationally labile, can be cis, can be trans, and the purple centers are under thermodynamic control. Pink centers are to be set by substrate reagent or catalyst control. What does it mean? It means that when we have these complex molecules, we need to understand that which centers are configurationally settled. For example, you have an umbrella. Just think about an umbrella. Umbrella is like this. So if you see inside, it is something like concave, and if you see from up, it's convex. Now, if there are two methyls in the upper side of the umbrella, then both will be definitely cis. It cannot be trans. So that is what is substrate controlled. So by default, if you generate two centers in the convex portion of an umbrella, there by default it's going to be cis. It cannot be trans. So it's something like substrate controlled by default. It's a topography of the molecule. And the one, if you want to synthesize one up and the one below, okay, it should be trans. It's again a substrate control. But now you want to make a cis and trans. So a trans in the convex type, there comes something like a reagent, substrate, or a catalyst control. So you have to control that stereochemistry. So when we come across these molecules, then first thing we need to identify that what is by default, and we call it thermodynamic control. It's already there, whatever you do, this will be cis. The next is how are you going to generate the trans when, or you want to selectively generate the trans when there is an equal possibility. That is what is reagent, reagent or catalyst control. Okay. Okay, so I'll just quickly pass in. Yeah. Okay. Okay, we have a tea break. Okay, then we'll come back. Okay. Thank you. Okay, I think you can join. There's tea already. Then you can have a tea, and you also have a tea. And if you have time, you can sit back, the MSc people, or you can go for your next class. Okay, but I continue with them.